So what is vector and what is scalar? And vector is a quantity that has direction and magnitude, and a scalar has only a single quantity, which is a real number or one magnitude or one direction or one temperature. So for example, like a time is a scalar, and how about the mass? That's scalar. And how about the temperature? That's scalar, right? And vector as opposed to scalar, what could be a vector? For example, let's say velocity. So velocity has a magnitude and direction. So let's say this rigid body goes to this way with a certain at 5 millimeter per second square. Then if this body moved the same direction with at 1 millimeter per second square, the magnitude are different. So velocity can be represented by the vector and also force, right? And later we are going to talk about the moment or torque, then that is also vector. So vector operations are very important in the solution of dynamical problem. And speaking of different types of vector, by default, when you say the vector, that refers to free vector. So in the free vector, we just consider the magnitude and direction. But sometimes we include the point of applications into the component of vector. Then the vector becomes bound vector. Sometimes, let's say, we have a rigid body and this one is rotating of axis. Then let's say this rigid body is rotating about this axis. Then there are certain points like that. So depending on where you apply the force here or here and here, given the same force, the torque may be different, right? So in a case, sometimes the point of applications should be considered when you define the vector. Then that can be a bound vector. And then another vector is a unit vector. The unit vector is like a free vector, but the magnitude is always the 1. So the unit vector is a vector that has one magnitude, but direction can be anywhere. So speaking of the vector notation, right now, let's say the vector, this is a starting point of one vector pointing to A. Then this vector is represented by this notation. So let's say this vector R. So I put this superscript, like arrow superscript. So that means this is vector. And then this is pointing to A from O, okay? So sometimes this vector can be represented by these two scripts on the left side, but these are the same. But I prefer using the first notations. And then this is just the name of a vector R, but you can name it. You can name your vector with whatever the name you want. Okay. And then so that's why if you want to add another vector, so let's say this is the point B. So this is point B. Then you can say, oh, this is vector R, pointing B from O. Okay. So that's vector. And then I told you that vector has a direction as well. So let's say this one has exact the same magnitude, but direction is opposite. Okay. Then let's say this is A dot. So I can say this is vector r a dot from O. But since two vector has the same magnitude, and this one is exactly the same as negative of r a from O. Okay, so the negative means the direction is opposite. And I told you about the unit vector. So in the unit vector means there's a vector. So let's say there's a vector like that. Let's say this vector has the same direction of this a vector, but if the magnitude is 1, so which means from here to here the magnitude is 1, then this one becomes the unit vector. Okay, so I can say my unit vector point 0 to a. So basically I can say my unit vector of this, or the vector A can be written like RA vector divided by the total magnitude R vector. That means the magnitude is 1 because we divide the R vector by the entire magnitude. However, the direction is the same. So this is a unit vector of this, our original vector from O to A. So on the right side here, so unit vector is magnitude 1. So that's why your R vector, original R vector, can be represented by the magnitude of its own. So from here to here, okay, is the magnitude of the total vector. And however, this magnitude itself, okay, this is a scalar. So since on the left side is vector, that's why we have to multiply the unit vector. So it has a scalar and a direction to become a vector. Any vector can be broken into different components. So right now the A vector here can be broken into the first and second and third components of vector. Then if you think about this one, right now we break vector A and B into three components: x, y, z coordinates. And as you see, the unit vector of x is I, and unit vector for y component is z, and unit vector for z component is k. In this example, a and b vector lies on the plane of xy. That's why there's no any z component vector in a and b vector. So if you break your a vector into I and j components, you can break down an x component of here. So this one is 9.66, and y component of a will be 2.9. So about here is 2.59. So in a symbol we can say ax component I and y component of j, something like that. And this one, the b vector is aligned to y. That's why there's no elements except the j component of a vector 7, which is 7 here. And this component concept can be useful when you do the vector summation or vector subtraction. So if I want to just add these two vectors. So right now, let's say this is a vector and this is a b vector. If you want to add them up, you can use graphical way, but if you understand the components, so think about a coordinate system like that. So this is x and y coordinate system, And then if you break your b vector onto x, so this is a bx, and in here should be by. And then if you break a vector along the x, so this one could be ax, and this one should be ay. So if you want to add a vector and b vector, and that's the same as b vector plus a. So if you just look at the component by component, so I want to just add a component, b component, and I, and y component of b vector and j. So that's the summation. If you subtract the vector from other vector, you can just thinking about component by its components. If I talk about one more things about the vector, so relative vector. In many cases, we use the vector for denoting velocity or acceleration, right? So, for example, let's say one object just moving this way with a certain velocity of a, and other object b is kind of moving it this way with a certain velocity of b. Then let's say if you stay with the object a, and then if you observed the motion b with respect to your position, the velocity of b may not be different from the velocity b observed from the original reference point. Let's say this is original reference point and x and y. Because you observe the motion of b with respect to yourself, and you're staying with the object a and moving together. So in a case, we can simply get the relative velocity, which means I want to get the velocity of b with respect to my a. So that can be the subtract of vector a from vector b. Okay. So if I just show this one is graphically, and let's say this is the vector a with respect to o, and let's say this is vector b with respect to o, then my relative velocity is pointing b from a. Okay, so this is a relative vector. So conceptually, this one shows the velocity with respect to not from the original reference point, but from your current position. That's what we call these relatives. And then speaking of the product of the vector, we have two product, dot product and cross products. This is the equations of dot products, and the result of dot product becomes scalar. It doesn't have any vector component in it. And then this theta is the between angle between two vector. And this dot product is commutative, so the order does not matter. And then if you compute the dot product using component of your vector, so a has x component I and y component of j, and dot bxi plus byj, then you use distributive law. So ax times bx I dot plus ax by I dot j dot, and ay and bx j dot I plus ay by j dot j dot. But if you look at the dot product of those unit vector, then I dot j become 0 because the between angle is 90 orthogonal, this one too. That's why finally we have only the component wise multiplications. So the result is just ax bx instead of x. I'm using here 1 and 2 and 3, and this is dot product, and this is dot product of the same elements, same components, and then this I dot I becomes just 1, and j dot j becomes 1. So the result is just product of the component, the summation of component products. How about the cross product? So cross product, the result of cross product is has a vector, the direction. So it's kind of projecting out from your plane. So let's say this is x and y, and this is kind of 3D space, for example. Then this should be your k vector, like that. And then the cross product follow a right hand rule, which means A cross product B means you have to you have to start from A, the B will follow that, so this is a B. So if you just used right hand rule, using something like that, so this is your A and this is your B. So your resultant direction is your thumb direction. Okay. But if you change the order, B cross product A, okay, so that means you start from B first and then A, like that. So if you use this right hand rule, your second index finger should be aligned with the B, and third finger should be aligned to A. Your thumb will direct it going down. So that's why the resultant direction will be opposite if you change the order. And then the result of the cross product using component of vector, then if you use distributive law, then you can multiply this one to here and multiply this one to here and this one to here, like that. Then you can just compute all the magnitude, and then if you look at the I cross product I, so I cross product I will be 0 because between angle is 0, and IJ becomes K, and then IK becomes minus J. So you have to understand what's the result of the unit vector cross product to get these finer equations for the cross product. Okay. So you just follow the right hand rule for IJK.